Alright, so let's try to sort of deepen our understanding of this notion of continuity. And in fact, we're going to ultimately tie our notion of continuity to our notion of derivative, which we are becoming so familiar with. So let's think about what continuity is. We've discussed this and introduced this to this point. And when you think about continuity, you probably think of the situations where a function is not continuous. Because we said a function is continuous if its graph is one connected path from left to right across the xy plane. So a function would not be continuous if any one of these three things happened. If you had a hole, if you had a jump, if you had an asymptote. The hole, you can't have one connected path because there's sort of that hiccup at that one point. The jump, you can't have one connected path by virtue of the fact that you have a jump. And the asymptote is not one connected path because you're going to have to pick up your pencil to sort of restart on the other side of the asymptote. So continuity, yeah, let me write this in here, is when a graph is one connected path from left to right. Well, that's how we've discussed it to this point. I want to sort of give us a more mature way of thinking about it, and my claim is that the three criteria that are listed here are three criteria which will guarantee that your function is a connected path from left to right when graphed. One, the limit exists, so your approach from left and right is the same. Two, the function exists. The function, there's not a hole there, there's something that actually exists there, but then importantly, while the limit exists, the approach from the left and the right are the same, and the function exists, the limit and the function have to coincide. They both have to be equal. So whatever the limit equals and whatever the function equals has to be equal themselves. So let's take a look at what this would, how this would sort of manifest itself. So let's imagine we're looking at that point there. If the limit exists, that means the approach from the left and the approach from the right approach the same function value. So here, the limit exists. Now the function has to exist too, so we've got to fill in the hole somewhere. But where we fill in the hole has to be where the two are equal. So the limit exists, and the function exists, and they're both equal. And this now provides not a hole, but in fact one continuous path from left to right. So if the limit exists, if the function exists, and the two are equal, then we have continuity. Note, each of our discontinuous cases violate this criteria. Take the hole. Does the limit exist? Yes, it does. Does the function exist? Yes, it does. Are the two equal? No, they're not. The limit is up here, and the function is defined below. So the limit exists, the function exists, but they're not equal, hence not continuous. You have to have all three in order to be continuous. What about the jump? Does the limit exist? No. You've already failed the criteria. What about an asymptote? Does the limit exist? Yes. The limit in this case is infinite. Does the function exist? As I've drawn it here, there actually is a function value wherever that point is located. So here the function does exist. Are the two equal? No, they're not, because the limit is up at infinity, but where the function is somewhere other than that. By virtue of drawing the dot where the function does exist, you can't draw that dot up at infinity, so the limit, infinity, the function, wherever it is, can't possibly be equal. So holes, jumps, asymptotes violate these three criteria. When you have these three criteria, the function is continuous. Okay, so a way to think about continuity: does the limit exist? Does the function exist? Are they both equal?